All right, guys, we're back. I'm starting the next chapter, chapter 4. And we learned in the previous chapter that you can find solutions to problems, or you can make your agent, you can implement its intelligence by doing what? Searching through data structures, right? And each one of those nodes in a particular structure represents a particular state of the world. And so we were going through and finding solutions to problems, having it solve problems by coming up with a sequence of actions. Okay, so in this chapter, we're going to continue talking about different types of searching algorithms, but the focus shifts a bit. Okay, and this focus is going to help us to understand or set us up for adversarial gameplay, I guess you could say, in the next chapter. But we're going to look at a different type of search or different type of searches, and the first part that we're going to look at is going to have to do with searches that are trying to deal with or finding a solution to a problem based on imperfect information or trying to use as little resources as possible. I don't know if you remember or not, but in the chapter 1 content, I was going through and saying, hey, they were limited by, early on they were having all these successes, and everyone was like, they're like, you can't do that, and they were like, bam, we can't, nothing but that. You can't do Y, and then they did it. They were in the zone, for some years, but eventually they hit some walls, right? And the walls had to do with hardware. A lot of it, you don't have enough memory or limitations on the programming languages themselves. Just resources are your biggest limit to what you can do. And so, in the beginning of this chapter, we're going to look at some ways that you could possibly address that, right? And it's going to boil down to, which approach you would take is going to boil down to, again, what the problem that you're trying to solve. Okay, hopefully you've learned that by now, that you don't start off just writing code, right? You have to do your requirements analysis, and you have to understand the problem that you're trying to solve, and then you have to come up with or find the appropriate algorithms and apply them to solve that problem, tweak them or whatever. So chapter 4 is about different types of algorithms that allow us to do different types of things using less resources. So the first thing we're going to look at is so-called hill climbing algorithms. Then we're going to look at some algorithms that have randomness built into them, right? So sometimes they're referred to as stochastic searches. So a genetic algorithm is going to be a great example of that. Simulated annealing is going to be another example of using randomness to help us get things going, right? And then we're going to talk about algorithms that will allow you to try to find a solution when you don't necessarily know everything there is to know about the search space, right? So, or the environment. The algorithms we saw before, they were like you had full knowledge of the environment, and you could always perceive everything, all the rules were known and all that. But what happens if maybe you don't have perfect knowledge of your environment? You have to make some contingency plans. Well, if I find myself in this state, then I'll do A or B, right? Or maybe a sensor or an actuator is broken or something. Or maybe, your Roomba starts spinning its wheels, it gets stuck, right? And so what do? Right? So we're going to talk about those types of ideas. And we're also, at the very end, we're going to look at a little bit of some basic rudimentary learning that the agent can do. All right, so it's a lot more involved discussion in the second half of the textbook on learning, and much more in depth, much more sophisticated, which we won't get to. But there's a class, I think, I can't remember the title of it. I've never taught it, but and it's new since we switched over to the semester system anyway a couple years back. And it's machine learning or deep learning, right? So this class we're kind of getting you the basics and some of the basic ideas that go into AI. So it's not, you're not going to be an expert in AI after just this course, obviously. Yeah, and also I'm going to take you through. I'm going to be doing some new videos here. You're going to see as you progress through the video content, the video lecture content, that it's going to shift a little bit. You're going to see a change because I'm going to be making new videos for you for this semester in the first half of the text, and then the second half I'll be able to reuse the material that I had from spring. When we had to abandon ship, and for everybody's safety. So if you're wondering where the picture goes, or if why my voice has changed or whatever, that's why. Okay. All right. So nothing's changed though. I mean, it's just I won't have to be making these new videos from scratch, and so I'll be able to focus on some other things, which will be nice. Right. So beyond classical search. Okay. So we've been talking about a certain type of search previously, right? Searches that led to solutions to problems that were sequence of actions. Okay. The focus of this chapter is on a different type of algorithm. Okay, or different types of algorithms. And these algorithms implement what are known as local searches. Okay, so what these algorithms do is they focus on an individual state, right? The paths don't matter anymore. Okay, the paths don't matter anymore. Okay, so it's just, can you get to a particular state, or can you generate a particular state? It's not a series of states, not a series of actions, it doesn't matter. Okay, so you'll see when we start talking about hill climbing algorithms. Okay, and basically, I mean, the benefit of that, if you don't have to worry about whole paths, you don't have to keep as many nodes in memory, or you don't have to generate as many nodes to be able to reconstruct those paths, those sequences of actions. Okay, so this is going to include some methods that are based on statistical physics. Now that sounds really, 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 I don't know, impressive, complicated. You're like, I don't know anything about statistical physics, right? And I don't know a whole lot about statistical physics either. It doesn't matter. We'll get through it together, right? And because we're not going to go into too much detail anyway, the math behind it. But at a high level, I'll be able to tell you about simulated annealing, which is a way to get a local search algorithm, a hill climbing algorithm, unstuck. Okay, and then you'll know what that means when we say unstuck. And then also genetic algorithms, really, really freaking cool. We'll be able to base, or we'll take a look at algorithms that are based off of, evolution, which I find fascinating anyway. I think evolution is amazing. And so then to use computers to leverage that theory to be able to solve problems. Oh man, fantastic. All right, so there was another thing here. This slide's missing a point, okay? And there should be an item here where it talks about, being able to find solutions for problems when you're working in an uncertain environment, okay, when there's some randomness in the environment, or when you don't have perfect knowledge of the environment. And so that big idea is that agents can anticipate what to do. And essentially, you might perceive, an agent might, this will be another type of algorithm that we look at, the and/or search algorithm. But this is going to be an agent that can perceive its environment, have a percept and say, okay, I'm in this state. But if it goes to take an action based off of that environment, right, based off of that state, it's not guaranteed that, if your choices are A or B, it's not going to be guaranteed that you will do A if you choose to do A, right? There might be, some kind of mix-up or some kind of problem where you might find yourself accidentally doing B, right? So I was talking about Roomba getting stuck, right? You expect Roomba's state to change from on carpet to off carpet, but what if you find yourself Roomba doesn't change state? The state goes from on carpet to on carpet, right? So you have to have a contingency. You have to have a plan, okay, for each of these percepts. And don't forget about the source code repository. Okay, in the Python implementation of the and/or algorithm, they use dictionaries to encode that plan. Okay, you can do a lot of different ways. Use if-else statements, use switch statements, but they had a really elegant solution where they were using dictionaries, and you could do a similar kind of thing, I suppose, with hash tables, since dictionaries are just implemented in Python based off of hash tables. Okay. So section 4.1 is about local search algorithms and optimization problems. So let's talk about that. So as I was saying, the path, a lot of times, depending on what you're doing, the path to the solution doesn't matter. It's the goal, right? So your goal might be, we need that final configuration for 8 queens, right? Is it possible? The question is it possible to arrange those queens in such a way that nobody's attacking each other, okay? Is it possible to arrange all of the components of a chip in a certain way, right? Can we fit everything on the chip? Okay, the order in which you put the queens on the board, or the order in which you put stuff onto the chip, the order in which you place stuff on the factory floor, doesn't matter. You just want the final configuration. You just want the final arrangement. Can you give me one, my AI? Okay, so these local search algorithms, all they're interested in is a particular state, and therefore trying to find a particular node that holds that state, that satisfies some target, that satisfies some goal, some state that you want to be able to create. So why, right? Well, if you don't have to worry about those paths, you don't have to use as much memory. You don't have to keep all those nodes in memory so you can reconstruct this sequence of actions, right? You don't have to build a complete tree and keep, all of the items or multiple pieces of that tree in memory. Okay, so this is great, for finding a particular solution when you've got these huge state spaces that the other algorithms we saw in chapter 3 just wouldn't be able to handle. Because if you only got so much RAM, you can't make 10 trillion nodes or keep 10 trillion nodes in memory, then you're stuck. Right? Even if a solution could be found, even if the algorithm you're using was complete, if you don't have enough memory to generate all the nodes to find that solution, you're screwed. It's worthless, right? So what can you do to get around that? Use a different type of algorithm that doesn't have to retain all those nodes in memory all the time. And that's what these local search algorithms are basically trying to do. So this is basically describing working with, or how we can work with, or how we can solve optimization problems. We want the perfect organization of items on the factory floor. We want the perfect organization of circuits on a chip. Right? We want to get all that stuff on there. Okay, and do that by having states evaluated. Okay, you have some kind of a function that evaluates that state, that scores individual states. Okay, because the algorithm is going to generate nodes, right, that have states in them, and then you evaluate those states within those nodes. But once you're done evaluating them, you're done with them. You can toss them, right? They don't have to stay in memory. Okay, so these searches are working on what the text refers to as a state space landscape. Okay, and this is going to include the location that a search finds itself in. Now this is going to be tough because some of this is going to be abstract. I'll try to help you out by drawing pictures, but the elevation, okay, and the elevation refers to the value that is given to you from the objective function or from a heuristic function. So what are your goals, right? So based off of the scoring of this objective function, and depending on what you're trying to do, how you frame the problem, you're either trying to find a global minimum or a global maximum within that state space. So what does that mean? Okay, that just simply means that of all the nodes you could generate, potentially for that represent that state space, right? All the nodes, remember nodes and state kind of are interchangeable, right? Because nodes are storing states. Out of all the potential nodes that you could generate, okay, you want to try to find, depending on what you're doing, your goals, find a global maximum. What does that mean? You want to find the highest value node, and therefore the highest valued state, and therefore the most desirable state, right? That might be the best configuration for the 8 queens, right? The best layout of machines on the factory floor, okay? Or depending on how you frame the problem you're trying to solve, a global minimum. So what that just means is you're able, with your algorithm, to identify that state, right, that has the lowest score, right? And which one you go with is going to basically be based off of how you configure that objective function. Okay. So what do local search algorithms do? They search the landscape. Okay. Now, these algorithms, hopefully, or I say hopefully, but you'll see some of the issues that we're going to have here in a second. Okay. So I'll just go with what the text says. Complete. Okay. So we want algorithms that are complete, so that way they always find the goal if it exists, if it's possible to have 8 queens on the board to where they're not attacking each other. Okay. Algorithms that are optimal. So what does optimal mean in this context? If you're searching for a global minimum, that is to say, the node that contains the state which has the smallest value, or the node that contains the state that has the highest value. It depends on how you frame the problem. Okay. Now, some of them may be complete, but not optimal. And this is what I was saying here a second ago. Because you might find there might be some configuration on the for laying out all of your machines on the factory floor. But there might be one that's better. Okay. And the algorithms may give you a configuration, but not the best configuration as scored by your objective function. Okay, and how could that happen? Well, because the search gets trapped at a local maximum and then quits. Okay, so let's take a look at this graph here, and then we'll look at the heart of these algorithms, and then we'll dig into it a little deeper. Okay, so what is this figure showing us? Okay, this is a one-dimensional state space landscape in which elevation corresponds to the objective function. Okay, so what does that mean? Okay, now these are nice smooth lines because it's a nice smooth graph, but as the algorithm is progressing, okay, a node would be generated, say here, okay, and they would be valued at a certain value. Let's say that we're looking for a global maximum, okay. So, you know, the node, we would evaluate it, and then we'd say, okay, well, that's worth 5. Okay, now there'd be a neighboring node that would be generating, like child nodes on the trees, right, from the previous chapter. And so you're only evaluating maybe one at a time, right, or maybe multiple nodes at a time. Okay, but there would be one node next to you which you would choose to then expand further, to continue the search from. So that node adjacent might be worth 10, right? So you're moving up the hill. And then lather, rinse, repeat. You find your next highest scoring or highest valued node is worth, I don't know, 20. Okay, and then you generate neighbor nodes off of that. Maybe there's one that's 30. Okay, but once you get here, generate adjacent nodes, and maybe they're all worth 32. Okay, so that's a shoulder, because you're always trying to advance the algorithm to the next highest. You know, you want to improve your position. You want to go from a node that's valued at 25 and therefore a state that's valued at 25. You want to continue the algorithm at a node and therefore a state that's worth 30, right? Well, if that node, that state that's worth 30, generates only generates child nodes or neighbor nodes that are worth 30, well, that's what a shoulder looks like. Okay, now if you know all the nodes that you've generated, if you get to a point where all of the neighbor nodes that would be generated off of a node that the search has gone through, has come across, if the neighbor nodes have a lower value, you've reached a maximum. Okay, now if that node happens to be the highest valued nodes out of all that could ever be possibly generated, that's a global maximum. Okay, but you can see here a local maximum. Well, what does that mean? Well, that means that it's got a value for that node, and therefore that state, that is higher than any of its neighbors that it could generate, but not as high as the highest possible state. Okay, and then you can have a flat local maximum too, where you've got a couple of nodes that, you know, a node in there whose adjacent children are the same value, but then those children's children have a smaller value. Okay, so this is what we're talking about. I'll draw you a picture of this here in a second. All right, so figure 4.2 is giving you a very, very simple, incomplete overview of how this works. Okay, so remember in chapter 3, we had the tree search algorithm, and then we had the graph search, right? But there were details that were left out because they were just trying to focus on, hey, here's the elements to these algorithms, and the difference is going to be, in which order you add nodes to the frontier, for example, right, into that queue, and in what order you take them out. Okay, and then tree didn't have a queue at all, right? So I didn't remember any states that I had before. Remember the explorer queue? That's what I was referring to. Right, so there were some details that were left out until we dug in deeper, right? So the same deal here. So function hill climbing, problem. So that just means all the necessary functions are in scope. So what does this return? A state that is a local maximum. So the way this is defined is that this is an algorithm that is going to progress through the nodes who have the highest child node values, right? So we're going up. We're trying to go up. This is hill climbing, not hill descending, hill climbing. So it's going to try to find the first state that doesn't have any children with a value higher than itself. Okay? So find a state that has inferior children all around, and then it'll return that state. And so that will be a local maximum. Didn't say global, right? Because it could be the case, just like here, right? Let's say we went in reverse. Right, let's say that our start point was over here and we were moving this way. Well, we would have hit a flat local maximum, right? But let's say that wasn't flat. Let's say that we started, say, here, right? We hit a local maximum. We don't, in either case, you didn't find the global maximum, so it says local maximum. Okay, so how does this proceed? Current. You make your node, you feed to that node the initial state, and then you got a loop. Okay, so what does this say? Right? Neighbor, okay, assigned to this variable neighbor, the highest valued successor of current. Okay, the highest valued successor. Might have 27 different successors. Okay, that just corresponds to like the frontier from the previous chapter's algorithms, right? So of all the child neighbors, okay, and since this isn't a tree, it doesn't really, the language doesn't line up all that much, but I'm using that term to hopefully give you some context. So all of your successors, right, all the nodes that can be generated based off of current, okay, the highest valued one, the one that has the best score, is going to be what we call the neighbor, okay? And if that neighbor, right, value is less than or equal to our current value, then we return. Otherwise, we update our current with the neighbor, and then the algorithm continues, okay? So what this is, essentially, is just the steepest ascent version of hill climbing search, okay? As this is written, this is the steepest ascent version, but we're going to see some modifications on this. This is just a loop moving to the highest valued adjacent node, okay? So this is hill climbing, but it's also the steepest ascent hill climbing because it's always going to the highest valued adjacent node or successor node. Now we're going to look at some variations of that try to get you off these shoulders, for example, right? Because you can get stuck before you get to your global maximum. And so there's variations of this which won't be called steepest ascent hill climbing. They won't be called, there'll be a variation of it where it can get you unstuck, or at least that's the goal. Okay, there's no tree. There's no tree. There's no tree. There's no tree. Okay, you only need a node and the result of that objective function. And you only ever consider the adjacent nodes that could get generated. Okay, there is no tree. So because of this, it's a local search, but it's a greedy local search because it's steepest descent. You're always going to go with the best neighbor node you can until you can't find any who are better than you. And then once you can't find any who are better than you, well, then you return U. Okay, hopefully I explained that okay. All right, I want to draw a picture of this. Okay, that's what I'm gonna do. I'm gonna switch over. So I'm gonna pause right here, and I'll be back with my whiteboard. All right, so we're back here, right? So the way this algorithm goes is you're starting off generating that first node, right? So I'll just draw a picture or whatever, and you'll have a homework assignment that has you do something similar. Okay. So you start off and you're generating some node. Okay. So I'll just label that as node A. Okay. So that is your initial node, and that initial node is going to have some value. Okay. And let's say that the value for it is, I don't know, 3, right? Now remember that value comes from an objective function, which is evaluating state that's inside that node, right? And so then you'd run your actions function. You'd figure out what all the actions were that you could run on that state A, okay? And then that would generate your successor states, which you then would store in nodes, right? Which would be adjacent, okay? So let's say that from state A, there's 2 actions which could generate a state B and a state C. Okay. Now your objective function says, oh well, state B is worth 2, and state C is worth 6. Okay. Now when we first started off, this was our current node. Okay. Now here's where the loop part comes in. You're evaluating the value of your initial state against the value of all the successor nodes. Remember, we talked about that. 2 successor nodes here contain state C and B. Well, state C, that's valued at 6. So that becomes the new current, right? And so at that point, these adjacent nodes could be deleted, right? You could remove them from memory. You don't need them anymore. Okay. Now, the search progressed from A to C. And so remember we were talking about that state space diagram? Well, we started here and then we just went up a little bit, didn't we? Right? We started at a value of 3 and then we moved up to a value of 6. Right? So we went up the hill a little bit. Okay? Now, from C, you could undo the action and go back to A, right? But we're not going to do that. You could go back, but the algorithm isn't going to take us back. Okay, so one of your successors could be the A state, but you might have a successor D, which is valued at, I don't know, 4, and then you've got another successor, E, which is valued at 8. Right? So guess who becomes our new current? E. And so we go up the hill even more. Now, all nodes other than the E node can leave memory. Okay, so why don't I just erase them to reflect that? Okay, there's no path here. I don't care about the path at all. I'm just trying to find the best state based off of my objective function. Okay, so let's say all the successor nodes. We got state F. Let's say that that's valued at 12, okay? And then let's say we've got state, I guess we came from D, right, which was 6. And then let's say that we got state G, right? And that's valued at 13, right? Well, guess what the new current node's going to be? G. So we keep on going. The other nodes leave memory because you don't need them anymore. See how much more memory efficient that is? I mean, if this was the chapter 3 algorithms, we'd have all these nodes in the frontier. We'd have to, keep track of our parent nodes so we can retrace our steps, right? All the pointers, follow the pointers back so we can get all the actions. You don't care about any of that stuff here. Okay. So let's say now that G generates its successor nodes, right? And where we came from was node F, and that was valued at 8. Now let's say one of the other successors is H, and that's valued at 2 for that state. And let's say another successor is I, which is valued at, I don't know, say 6, right? Well, guess what? We just found a maximum. Okay, and then if we were to continue, right, the highest, if we were able to continue, the highest neighbor is 8 over here, and then there'd be 6, right, for I over here. Well, we found a maximum. This state, that right there, has got our best state that we found based off of this simple version of the algorithm. Now, if we were able to move over to continue, if we were able to continue, say, we changed the algorithm up a little bit, and we were able to come around and say, all right, well, let's continue generating off of the I node, right? Let's say we could do that, right? Well, then we have our, what was it? I can't remember what the letter was. So we'll just say it was F, okay? That was valued at 13, okay, fine. Because we could go back where you're coming from. But let's say that there was another node with state J, and that one was worth 22. Right? Well, guess what? We didn't find that one. That's the problem. So this right here, let's say that no other node anywhere else that could be generated was worth more than 22. Well, this is a global maximum, right? And this right here, that was worth 13. That is a local maximum, okay? Now let us say, crap, I drew myself out of space. So let's say that the adjacent node over here, let's say, let me delete our landscape, okay? So I can show you what a shoulder could look like, okay? So we generated a node that was worth 13, right? And I'll call that node N, okay? So if I had a node N worth 13 by my objective function, and I generated successors, well, one is going to be, worth the 8 from where I came from. But if I had another one, call it O, that was worth 13, well, then there's 13 here, right? That's what a shoulder looks like, okay? Now, it could be the case that there are no other nodes with a higher value than 13, okay? In which case, this would be a maximum, right? A shoulder maximum, but which state is better? Okay, so that's the problem. Let's say that there was, right? Let's say that we're at N and we generated the O, and I guess I'll just call this M. But let's say the successors for O were N and P. And let's say that P was worth 16, right? Then the space looks like this. Right? And so now this shoulder is a local maximum, but it's not the global maximum, right? Because P is worth 16, and maybe it is the global maximum. Maybe that's the best state we can find. But guess what? We got trapped in our search here because the algorithm stops when you don't have anybody with a higher value than your current node. So when the N was considered current, its biggest neighbor was 13. The algorithm's over, right? It would return the state that corresponds to N. Now, is there some way we can get ourselves off of this shelf, off of this shoulder, so that way we can try to find the global maximum? That's where we're going to go, because there's going to be strategies that are variations of the local search, right? This hill climbing search that try to get around this. Now, could be the case, like let's say we inverted this and we're always looking for the smallest value, right? So let's say that we started off with a node whose state was valued at 20, right? And then its best successor had a value of 15, and then that guy's best successor had a value of 4, right? And then that state down here, that node for the value of 4, its successors are the one that was 15, and then one that was 12, right? Well, now this is a minimum, okay? And then you can have a global minimum. You know, you could have a local minimum, right? In this case, whereas this is the global minimum, right? So what's the difference between maximum and minimum? It's just what you're trying to do, right? Do you want the highest score or do you want the lowest score? That's all, right? So part of the struggle is, how do you deal with these shoulders? How do you try to maximize your chance of finding a global maximum and not settling for, you know, a local minimum? I gotta be careful with how I draw this, right? You want to try to get the global maximum, okay? Not settle for a local if possible. So is there a way we can try to accomplish that? Well, yeah, right. So what I've described so far has just been the steepest hill climbing ascent algorithm, and I pointed out some of its possible flaws. Okay. All right, let me go back to slides here. I'll pause and we'll switch right back over. It's incredibly risky what they're doing. If one in that room has it, they all do now. You realize if one of you guys has it, you all do now. You just killed your parents. The reason has it, you just killed your parents. All right, so we're back here. The text goes on and talks about you know, an example of the 8 queens problem. Okay, and these local search algorithms, you know, you have to have a complete state formulation. So, you know, you have to specify, you know, everything about the states that are possible. Okay, and the rules. That's basically all that means. So let's talk about 8 queens, right? So each state is going to have 8 queens on the board, 1 per column. How do the successors get generated? Right? You move 1 queen 1 space in the same column. Now you're not keeping track. You don't need to keep track of the actions that cause that to happen, right? You just have to be able to generate the successor states. Remember, you don't care about paths. Right? The solution isn't an action. The solution is the highest valued state. Okay? Heuristic function h, call it h, it's going to count how many pairs are attacking each other. So in this formulation, you're looking for a global minimum. You want 0 pairs of queens attacking each other. Okay, that would be perfect. Okay. So in this case right here, on figure 4.3, on the A board, right, this has got a heuristic cost estimate. Its objective function could report 17, right? And that is going to be valued off of, how do I want to put this? Right, so it has a cost of 17, okay, because there are 17 different ways that the queens can take each other here. Now, what are all these other numbers showing, right? If you were to move this queen here to this square here, right, that successor then would be worth 15. Okay, if you were to move this queen here, that successor state would be worth 14. Okay, now in B here, okay, what we have is a local minimum in the 8 queen state space. Okay, so there is a local minimum. Okay, because why? The value of this state is 1. Okay, why? Because there's 1 pair of queens attacking each other. Okay, it's not the perfect state. So this would be a minimum, right? If depending on the order in which the states were generated, okay, it would be a local minimum. The global minimum is 0. Okay. Now it could be the case could be the case. How could we get past a shoulder? Okay. What if you've got two adjacent nodes that have the same value, right? And that's not a shoulder. So let me step that back. Okay. Let's say that you're trying to continue on with your search, but 2, 3, 4 successor states have the same value, right? So which one do you pick? Flip a coin. Right? So we only care about what's best right freaking now. Now the thing is these things can actually perform really well, not just in terms of the amount of memory that's being used, but going from a really bad state to a really good state, that can happen actually pretty quickly, right? But as I was saying, they can get stuck, right? If you get stuck at local maxima. Okay. Don't want to talk about figure 4-4. Yeah, I mean, this is just basically telling you about ridges, right? And why ridges in the state space can be bad, because it could be the case that you get stuck within a particular portion of the state space to where you're, maybe you're at the top right here, right, top of this ridge, but further on the state space you have a global maximum, but you're stuck at this local maximum, right? Or maybe you're stuck here in your search, but which direction do you go, right? Maybe these two states have the same value. Okay, so do you go up? Do you go which one do you go to? Right, you'd have to flip a coin. Okay. All right, so you've got plateaus, and those are flat areas. Okay, we talked about one, a shoulder, and shoulders allow you to have progress. Right, we saw that. Okay, if you could get past the shoulder, you could go on and find your global maximum. Right, and this is, the objective function value over time. And this is the state as you're generating the underlying state space, or as you're exploring it as the algorithm proceeds. Okay, so another example of a plateau is a flat local maximum or minimum. If you're trying to find the smallest value. So this is a flat local maximum right here. So these are two examples of plateaus, but they're two different types of plateaus, because from the shoulder you could progress if you get past it, right? Because you just have to move past one node and you're there, right? But you can have multiple nodes that are all adjacent to each other, and the nodes that are adjacent to them, they have no bigger value, so you're just stuck. There's no way you can get off of that. Okay. Now, as it turns out, here's some numbers for you. Steepest descent hill climbing without any modification. If you were to write your own program for Make Queens, that actually could be a really fun programming assignment. I'll have to think about that. It gets stuck in one of these plateaus, okay, or at a local maximum, or I guess in this case minimum, right? Because we're trying to find 0. So about 86% of the time, if you do the math on it, and we'll just take the textbook's word for it because we don't care to do the math on it. I believe them. They probably know what they're talking about. But here's the thing. If it doesn't get, when it doesn't get stuck, okay, when it works, you can find the goal, or the algorithm can get itself stuck. You can find the goal in maybe 4 steps. 4 generations of nodes, of adjacent nodes. Boom, 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 boom. Done. Or maybe on average just 3 steps you can get yourself stuck. So what's the benefit here? Well, we know that you lose or you use up a total far less in terms of nodes that actually have to be memorized at any one time. And the ability to find a solution is very fast. In the 8 queens problem, there is the possibility to generate 18 million possible states, 18 million possible nodes. So the underlying state space is huge, okay? So, but when it works, right? 4 steps and you found a solution. Right now it gets stuck 86% of the time, but the other 14% of the time, man, 17 million nodes. You just have to look through 4 of them, basically. You know, and their successors, but that's it, right? 17 million nodes. Imagine that tree compared to this. Okay, very, very, very fast, but crashes a lot, right? Why does it crash a lot? Because it gets stuck, right? All right. So figure 4.1. Right? Wow, that goes a little back. Here we go. Right. So right here, you can get stuck. Right. Right here, you can get stuck. Okay. On these plateaus. But if you could get off of them, if you could get off those plateaus, okay, then you could continue on the search and then find a better solution than what you're stuck on, right? So what can you do? Well, let's do a sideways move, okay? And you want to hope that you're actually on a shoulder rather than on one of those flat plateaus, okay? So maybe you just simply change the algorithm to say, well, I'm going to make the current a successor node that is greater than or equal to what the current node's value is. Okay, right? Problem with that is that it could be a loop, an infinite loop. If you're on a flat local maxima and it's not a shoulder, you'll just bounce back and forth. The algorithm will just loop back and forth, moving from node to node to node. Just generate node, 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 generate node. Okay, so how can you get around that? We could have a counter. If you bounce back and forth 10 times, stop and return the state of whatever node you last examined, right? So for 8 queens, if you put in a 100 move limit, the success rate goes from 16% to finding a solution to 94%, right? Because with that 100 move limit, okay, you could have a shoulder that's 80 nodes or 60 nodes or whatever, right? Some number of nodes. And so doing the sideways moves, is eventually going to get you to a node that has a greater value than where you were at. Okay. All right. Now, cost you a little bit more. Okay. So from 4 to 21 steps for success in doing and for making this change. And then for failing, on average, you don't fail in 3 steps, you fail in 64 steps, right? So, it's a little bit slower in that regard, but look at the odds of finding your solution. It gets way, 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 way better. Okay, finding your goal. So here's a couple of additional variations. Okay, so there is a variation called stochastic hill climbing. Okay, it's not steepest ascent anymore, right? Because steepest ascent would just say, I'm going to go with the most highest increase in value I can, right? So if you've got 3 successor nodes that are all more valuable than the current node, you would go with the one that is the absolute best, right? So if your choices are between 8, 10, and 12, you're going to take 12 every single time, okay? But if you've got 3 uphill moves in the stochastic hill climbing algorithm, then what you do is you randomly pick among the 3, right, of those 3 different nodes that improve your current position. Now, the randomness, you can tweak that, you can fine tune it, and you can base it off of, for example, the degree of ascent. Well, what does that mean, right? That just means the difference between the current node's value and the improved node's value, right? So if the current node's value is 5 and one of the successor node's value is 7, well then there is your degree of ascent, your rise over run, as it were, okay? 7 over 5, okay? And then you might have another node, another successor node that has a value of 10, right? So what's the difference? 5 and 5, right? 10 over 5. So then you could have your random probability be a ratio of those differences. Okay. Now, the solutions, again, you're going to find them. It slows things down. As you add this complexity, the search does slow down. But it does lead, usually, to solutions that are better than steepest ascent, because you don't crap out on a shoulder. Okay. And, well, I say that. I mean, you still could, but you could have a path that right now seems less valuable, right? A successor node that seems less valuable. But if you choose it, the following node is more valuable than anything you could have had earlier. Hopefully that makes sense. Okay. So our first choice, hill climbing. This is implementing this. This is a variation of it. And what it does is it just randomly generates successors, okay, until it finds one better than your current node. Okay, now this is good when you have a whole bunch of possible successors, right? So you don't just process your actions on your current state in a strict order, okay? You could randomly apply actions to your current state to generate the successor state, okay? And you just keep doing that until you find the first one that's better than the current state, okay? Now, that randomness gives you some of those benefits of finding better solutions, but since there's randomness there, and you just take the first best, the first improvement, the first better node that comes along, you might not look at all of your successors. Okay. All right. So those algorithms are incomplete if you're looking for global minimums and maximums. Why? They could get stuck at a local minimum or maximum, right? And so they won't find the best solution. Okay, they won't find, if your goal is to find the absolute best, your global maximum, global minimum, it's not going to be complete. You're going to get stuck with an inferior product. So how can you get around that? Okay, how can you get around, possibly being stuck at a local maximum? Well, a variation of the hill climbing algorithm is the random restart hill climbing. So what this does is it'll randomly restart. And once it gets stuck, once you hit a plateau and you can't move on, or you are at just a minimum, okay, or a maximum, depending on how you look at it, once you get stuck, then you could randomly generate a new initial node. Okay. So if you give it enough chances to do that, say, okay, I'm going to run you, you find the best that you can 5 times, and we'll keep the best state out of those 5. Right? Once you hit a place where you can't continue on, we'll note that state, we'll note that score, and then we'll move you. We'll randomly generate another starting node for you, another initial state, and then run you again. Okay. So if you have enough chances, right? If you give it enough chances, enough random, if you set that limit high enough, okay. I mean, you can brute force it, right? Let's say that your underlying state space could generate a possibility of 27 nodes, and you build in, 10,000 random restarts. Eventually, right? Probability dictates that you will generate a start state that is your goal state. And so you'll find it, right? It'll be complete if you provide enough random restarts, okay? That's not very, as it says, satisfying. It's kind of like, well, that's kind of gross. Yeah, it's gross, but it is complete, For 8 queens, it's very, 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 very effective. So you'll find your solution, right? This thing will allow you to make those sideways moves. If you do incorporate the ability to deal with sideways moves, you'll find a solution in about 25 steps. You will find a solution, and you'll find it in 25 steps. So what does that translate to? Well, when they did the testing in the textbook, right? If you've got 3 million queens, we're not talking about the 8 queens problem anymore. We're talking about 3 million queens. Imagine a chessboard big enough to put 3 million queens on. That would mean 3 million columns by 3 million rows. Run this algorithm. At least when they ran this algorithm on the hard, or at the time the text was published, they found the solution where no queen out of 3 million was attacking each other on that huge board in less than a minute. Okay, so how successful you are, it's going to depend on your state space. NP hard problems, usually there's an exponential number of maxima or minima that the algorithm can get stuck on. Right? But regardless, okay, if you take all of these factors into account, you may not find the best, you may not find the global maxima or minima, but you can find a pretty good one. Right? It may not be the absolute best 100% perfect arrangement of items on the factory floor, but it'll be pretty good. All right. So simulated annealing. Let's talk about this, and then I'll get us up to genetic algorithms, and I'll put a cut in here. Okay. So simulated annealing. Here's the thing. All right. So if you've got a hill climbing algorithm, a version of it that can't go downhill, right? You will get stuck at some local maxima, right? You can get stuck at some local maxima, and therefore never finding the global maximum. So in that regard, you can say they're incomplete, because if your goal is to actually find the absolute best possible state, unless you deal with it, you're not going to find. You may not be able to find it. You're not guaranteed to find the best state every single time the search runs, so it's not complete. Okay. Now, doing that random movement that we talked about a second ago, it's complete, but it's inefficient as heck for what we talked about, right? So what simulated annealing strives to do is to combine the two ideas, right? Put some randomness in there, and have the ability to move downhill. Okay, so the idea is gradient descent. And what you're trying to do is you're trying to minimize cost. So the example they give you here is, let's say that you had, see if I can describe this, right? Let's say that you had a bumpy surface, right? Let's say that you had a very poor surface, and there's a bunch of pits. Okay, you had a piece of cardboard or some kind of piece of plastic, and there's a bunch of pits, okay, all along the surface, right, with varying depths. And then you got a ball that you drop on top of that surface. And your goal is you want to get that ball into the deepest pit. And so how can you do that? Well, you can shake the surface, okay? You can, if you've got your ball in the shallowest pit on one edge of your surface, and the deepest pit is on the far side of the surface, well, then you might really shake that thing hard. You might really just give it a good jerk, right? So that way the ball will fly as far as it can in one move to get the ball as close as you can to that deepest pit. Okay, but once you got closer to that deep pit, okay, then you're not going to do it as hard, are you? Because that would send the ball flying in the opposite direction of what you want. So you maybe give it just a little bit of a shake, right? Maybe just a little bit of a toss, just to get it to jump over one pit to get into the deep hole. Okay, so that's kind of the idea here. That's the example, right? So I'll just go through and highlight this algorithm so we can finish this up, and then I'll let you trace through the code and save any questions you might have. I'm going to start transitioning more and more away from absolutely holding your hand on every algorithm at this point. Okay, so here's the idea. Okay, there's the innermost loop. That's like the hill climbing we've seen so far. Okay, but you're not going with the best move every single time. You're going with a random move. Okay, now if the situation is improved, go with it. Right. So if you are if your current state has a particular value, and you're going to pick a random adjacent state that you could move to, that the search could progress to. Okay, you're going to pick that random one if it is better than where you're at. Okay, otherwise pick another. Right. So here's a way of looking at it. Okay, and the textbook talks about delta error or delta E. So if your position is better, right, if it's an improvement, take it. Okay. Otherwise, you can roll to see if you should accept whatever the inferior position is. Okay. Yeah, I mean, so if your situation does not improve, okay, so let's say that all of your adjacent states, all of the successor nodes, because you're at a local minimum now, or maximum, sorry, at a local maximum, maybe at a plateau. Okay, so you generate your successor states. There's nowhere else to go. Okay, you can't go up. There is no up. There's only down. Okay, so what happens is you pick one of those. Okay, and then based off of some value, off of some variance. Okay, if the value is that variance value is greater than zero, that evaluation is greater than zero. Okay, take it. Otherwise, roll to see if you should take it. Okay. All right. If you don't, then the state remains unchanged. Time marches on. And then the temperature. Okay, the temperature is that measurement that we were talking about. Updates according to the schedule, according to a schedule. Okay, so you're going to see this math here in just a second. So as those choices are made, okay, the randomness, the amount of randomness starts to shrink. Okay, and that's going to be based off of how bad the successor nodes, or those choices that lead to successor nodes, are. Okay. All right. So here's the algorithm, and so let me point this out. Right. Let me point these parts out. All right. So go ahead with your very first node, right? Your initial state. So here's time. That's T. Right. So that's a loop. Time is advancing. Okay. So temperature is T. So you have a schedule function that you feed the turn into, and then that returns some kind of a temperature. And so you would define it. So as time passes, this T value varies. Okay. Now eventually it's going to get smaller and smaller and smaller and smaller and smaller and smaller and smaller until it hits zero. Okay. And once it does, then whatever the current node is, that's going to be, you're going to settle for that state. That's the one you're going to go with. Otherwise, randomly pick one of the successor nodes to become your current. Okay. Delta E is that next node, that randomly selected node's value minus the current node's value. Okay, so my node's value, one of my randomly selected successors, I take the successor's value and I subtract my value. Okay, so if that difference is greater than zero, then that randomly chosen successor node becomes the current node. And we do it again. Otherwise, if that's not the case, if this is false, then we'll only make the next node our current based off of a probability that is based off of this formula here, right? E raised to that delta E divided by the temperature. Okay. So there's randomness built into it, okay, and this randomness, this probability adjusts as the search continues. Okay, so that schedule function, that's going to determine the value of the temperature as a function of time. That's what I was saying. Okay, so this is representing units of time, whatever they may be. Okay. All right, so I would suggest grab a piece of paper, you know, make up some schedule, and just go through a couple iterations of it. All right, so let me talk about local beam search, and we will be done. I'll put a cut in. Okay, so here's the thing. Right? The big idea behind local beam search, you don't have just one current node. You have multiple. You have k current nodes. Okay, so instead of just one, you got multiples. Okay, and the search is proceeding based off of all those multiple nodes. Right. So far we had in our different variations of the hill climbing algorithms, we had the one node, and then we judged to be, you know, that's our current, and then we'd have some way of figuring out who the next current is going to be. Okay, we just have one of them. With a local beam search, you got k, you know, 2, 3, 10, you know, whatever. So it's not as, it says here extreme, it's not as rigid, right? So you're going to start with a handful of states, right? And so the search, you're going to have a handful of searches happening concurrently in parallel, right? So you've got k randomly generated initial states, and then you've got k iterations of the search happening all at once in parallel, right? This would be a perfect candidate for a multi-threaded application. Okay, so the algorithm, the searching algorithm, proceeds for each of those states, and if at any point one of those is the goal, well, then you're done, right? So you start with the k randomly generated states. If any of those are the goal, just right there, you're done. Otherwise, replace those k initial states with k best successors and repeat, right? So again, the big idea is you've got k initial nodes, you pick the k best successors out of all of them, right? And then those k best successors become your new k current, okay? Hopefully I explained that okay. If not, rewind, watch it again, send me an email, stop by my office hours, okay? You'll see this play out. Keep this in mind. Hint, hint, hint. Keep this in mind because genetic algorithms, which are going to be one of your programming projects, they are a variation of a beam search, okay? All right, so yeah, parallel search threads, right? And the algorithm does its best to abandon these worst searches and focuses on where the progress is greatest. So if each one of those searches going in parallel is just a steepest hill or steepest descent hill climbing search, they'll get stuck. You know, some of the threads, the search threads will get stuck, fine, then you're done with those guys. And then the other threads can continue on their merry way. Okay? But if they don't get stuck, right, what ends up happening is those states become concentrated, right? As the searches continue on, right, they start generating or they start concentrating into smaller and smaller and smaller and smaller sets of nodes, okay? And at that point, it just, the performance kind of degrades because you're only, at that point, all the searches are focusing on, you know, moving around through, you know, this smaller set, this subset of the state space, okay? So stochastic beam search, variation of this is to instead choose k random instead of the best k. So stochastic means random. So instead of the best k, go with a random number of k successors. Okay, and so then the probability increases according to that successor's value. So this is kind of like natural selection. This is going to lead us into discussing genetic algorithms. So let me take it even further and be even more clear. A genetic algorithm is a form of a stochastic beam search. And hopefully you'll be able to see that, right? Because we're going to start off with a randomly generated pool of individuals within our population. Each one of those individuals is going to represent one of these states. And each one of those states is going to evolve, okay? And so that evolve is just a representation of transitioning from one state into another, from going from current state to next state, okay, and so on. And, you know, we'll have 50,000 individuals, you know, 100 individuals, whatever, okay? And each one of those individuals, each one of those individual states in the population of states, the search is progressing on, Okay, so there's your parallelism. All right, so yeah, so I'll put a cut here. We'll come back and in the next video we'll talk about genetic algorithms. And they're a type of stochastic beam search, okay? All right, and I'll draw some more pictures for you and all that. Okay, thanks for watching. We'll see you in part 2.